Hi everyone. Today is our first video for Chapter 4, and to start off Chapter 4, we're going to start learning about something called implicit differentiation. And in a minute we'll get to when we would use this, but for right now I want to look at this first example. It's asking us to find the derivative for the following function. And so here we have our function defined, and the first thing I want you to notice about this, which hopefully you have, is that it's not solved for y. So y is not by itself. So the first thing I want to do before I try and differentiate is actually go ahead and get y by itself. And so this one's pretty easy to do that. If I subtract the 3x squared from both sides, then I'll have y by itself. So I'm going to go ahead and do that. So in this first step, I'm just rewriting. So I have a negative 3x squared plus 2x minus 7. So now we have a really simple polynomial function, and we can take its derivative using the power rule. So we get negative 6x plus 2. So that's a pretty easy function to deal with. Implicit differentiation is going to help us with functions where it's not solved for y, and either it's difficult to or maybe we don't even have a way of solving for y. Implicit differentiation is still going to allow us to find a derivative for that function. So we're going to take a bunch of notes and then we'll revisit this example and see how we would differentiate it using implicit differentiation. Okay, so first in terms of some vocab and some steps, implicit notation for a function is just when a function is not written with y by itself. So for example, we have the problem 1 that we did above. I could look at a problem like x plus y equals 0, or x squared plus y squared equals 4. Those would be functions that are implicitly defined because y is not by itself. Okay, and so sometimes up above we were able to solve for y pretty easily, but sometimes it's going to be much easier to take the derivative of a function that's defined implicitly if we don't have to solve for y first. Okay, and that's exactly what this implicit differentiation is going to allow us to do. So in these types of problems, we know that y represents a function. So we need to treat it a little differently than we treat x when taking the derivative. So every time we take the derivative of y, you will need to apply the chain rule and multiply by dy dx. And we'll see what that means as we get into some examples. So here are the steps for how we're going to implicitly differentiate functions. So the first thing we're going to do is differentiate both sides of the equation with respect to x. Then we're going to collect all the terms with dy dx on one side of the equation. We're going to factor out the dy dx, and we're going to solve for dy dx so that we end up with a derivative of y with respect to x. And this is probably the biggest point here, because now we have a lot of methods to differentiate functions, and so it's going to be important to know when to use these different methods. And so for implicit, we can tell we need to use this technique because the function will be defined implicitly. And really what that means, it won't be written as y equals. We'll have a function where y is not by itself, and that is what's going to tell us that we need to use implicit differentiation. So let's go back up to our first example and try to go through these steps and apply them to this example. So in this case, we're not going to rewrite our function first. We're going to use implicit differentiation. So our first step said to differentiate both sides of the equation with respect to x. So now, my first term is easy to deal with. I know it's 6x. Now, because this term has a y in it, we need to treat it a little bit different. So the first thing we're going to do is just take its normal derivative. So in other words, since my variable is y, I know my derivative is just 1. But now, because I have a y, this is where that chain rule piece comes in, I need to take the derivative of y with respect to x. Now on the right-hand side, the derivative of 2x is just 2, and the derivative of negative 7 is 0, so that drops out. So now I want to get all my dy dx's on one side of the equation. In this case, it's pretty easy. I'm just going to subtract 6x from both sides. So I'll get dy dx equals a negative 6x plus 2. And you can see that either way we take the derivative of that function, we get the same answer. So now let's take a look at some other examples. The next 4 we're going to do, either it would be more difficult to solve for y, or like I said, in some cases, we may not be even able to isolate y. So let's look at number 1. So we're going to differentiate everything with respect to x for our first step. So my first term, my derivative is 2x. For my second term, I'm going to take the derivative just following our normal rules. So I have plus 2y. But now I have to differentiate y with respect to x, and that's where my dy dx comes in. I differentiate the right-hand side as well. The derivative of 25 is just 0. And so now the only work left to do is to get that dy dx by itself. So I'm going to subtract 2x from both sides. And now to get dy dx all by itself, I'm going to go ahead and divide both sides by 2y. And then the only thing else I notice is I can factor out this cancel of 2, and so my derivative is negative x over y. I'm actually going to skip to number 3 next, because the next couple problems actually get into some product rule and more advanced chain rule problems. So let's do a more basic example first to make sure we've got this process down, and then we'll move into 2 and 4. So for number 3, here we go. We're going to differentiate. Again, the first round, whenever I have a y, I know I'm going to have a dy dx, but the first thing I do is just differentiate like normal. So I'm going to use my power rule here, and I get 10y. And now I have to differentiate y with respect to x. My second term, my derivative is going to be a cosine y, but again, because that's y, I'm going to differentiate y with respect to x. And then on the right-hand side, I get 2x. So now in this case, this is the first time we've had 2 of these dy dx's on one side, so I'm going to factor them out, so ultimately I can isolate that dy dx. So if I take a dy dx out of each term, I have 10y plus cosine y, and that's equal to 2x. So now I'm going to divide both sides by 10y plus cosine y, so that I get dy dx equals 2x over 10y plus cosine of y, and that's my derivative. Be careful that you don't cancel this 2 and factor out the 10. Since both of these don't have a factor of 2, I have to leave it where it is. All right, let's jump back up to 2 now. And so when I look at this problem, I notice a couple of things. First of all, I notice that it's not set equal, y is not isolated by itself, so I know I'm going to have implicit differentiation. I'm also noticing that because the argument of tangent isn't just x, it's got a y in there, I'm going to have chain rule involved in this problem as well. So let's go ahead and get started. First thing I'm going to do is differentiate x. At least that part is easy. I know that's 1. Now I'm going to differentiate tangent. So I know I have secant squared. And my argument for right now is going to stay the same. Now, using the chain rule, I have to differentiate my argument xy, and that is actually going to trigger product rule. So I'm going to take x times the derivative of y with respect to x, so that's just dy dx, and then plus, I'm going to take my y times the derivative of x, which is just 1. And the derivative of 0 is just 0. So that's going to finish off my first step of the equation. So now I know my goal is to get dy dx by itself. So I have to get it out of these parentheses. So the first thing I'm going to do is move my constant over. So now I have 6 secant squared of xy times x dy dx plus y, and that's equal to -1. Next, I'm going to divide by secant squared of xy, get me one step closer to isolating what I need. So I'll have left x times dy dx plus y, and that's going to give me -1 over secant squared of xy. Now, I'm going to go one step further. Instead of leaving this fraction here, I'm going to rewrite that right-hand side. I'm going to make that, I know 1 over secant is cosine, so I'm going to write this as the opposite of cosine squared of xy. So now, I'm almost there. If I subtract a y from both sides, get x times dy dx equals negative cosine squared of xy minus y, and then my last step is just to divide both sides by x. And so I get negative cosine squared of xy minus y all over x. So that one was pretty hefty because we have implicit differentiation with chain rule with product rule. All right, we'll do one more for this video. So now we have implicit, and you can see pretty quickly here we're going to have some product rule as well. So I'm going to take my first term first, and this is going to generate a lot of terms here. So I'm just going to underline my first term in purple, and I'm going to do that differentiation in purple too, just so we can keep track of where all these terms are coming from. So I'm going to do product rule on my first term. So I have x squared times the derivative of y, which is going to give us a dy dx, plus y times the derivative of x squared, which is 2x. Then I'm going to take my second term. So I have plus x. Now my derivative here of y squared is going to give me 2y times dy dx plus y squared times the derivative of x, which is just 1. And that's all equal to the derivative of 6, which is equal to 0. So now I'm going to collect up my terms with a dy dx. So I notice I have one here and this whole term here. And I'm going to keep those on the left-hand side of my equation. So x squared dy dx plus 2xy dy dx, and I'm going to move everything else over to the left-hand side. So my 2xy moves over, or I'm going to move those to the right. Goes over to the right, and then my y squared is going to move over, and it'll become a minus y squared. So now I can factor out the dy dx out of both of my terms on the left-hand side. I have x squared plus 2xy in parentheses. I'm going to copy down the right-hand side. And now if I divide both sides by x squared plus 2xy, I will have my derivative. And again here I'll caution you to avoid the temptation to factor out that 2xy because this is addition and subtraction in between and not multiplication. We cannot cancel out that factor. So this is a pretty good overview of implicit differentiation. Again, it gets a little trickier when we get into those product and chain rule problems, but we'll be doing some more practice with that tomorrow.